all sites, and in particular, we're looking for sites that are not variable within a taxon. Now, you may consider a taxon to be a species, but you also might consider a taxon to be a genus or a family if you're looking at deeper time relationships. And we're looking for sites with no variation because if there's variation, you have a greater likelihood the phylogeny sites are derived from phylogeny genes, and so that increases your noise. So we're trying to filter out a lot of noise. We're going to remove sites with too much missing data. This is up to the end user, how much missing data you're willing to deal with. And you end up with an alignment of what should be mostly informative sites. So this is a question everybody wants to know. Does it actually work? And I wouldn't be here if it didn't work. So I did a bunch of simulations. We have 4 trees. This is the simplest tree, as you can see. And then we have 3 trees that have varying levels of varying ratios of intermediate node distances here. So the results, so each of these panels here is how divergent your taxa are. So from least to most divergent. And you can see for less diverged taxa, you recover a lot of sites. So this is a 1 million base pair genome. It's very, very, very small. You can get a lot of data for a 1 million base pair genome. Surely you can get a lot more data for the human genome. Of course, as you get more diverged taxa, you do lose some information. So each of these are the 4 trees. But keep in mind that in a lot of cases, in most cases, you'll have some regions of the genome that are not highly diverged. So you will end up with good data sets. And all of these for the simulations are true positives, so we don't get any false positive data. If you break this down by depth, this is again what you expect. As you go deeper in the tree, you get fewer sites that help you recover the tree, particularly as you get to highly diverged taxa. But of course, again, for relatively conserved regions of the genome, which you will have even across the decoy eukaryotes, you get quite a few sites that help you recover the tree, even for deep relationships. So to look at some actual empirical data, this is the phylogeny for apes. Now, since this is a very well-established phylogeny, what we want to do is actually recover the known phylogeny, and in fact, we do. So this is what you expect it to be. So this is great. This is constructed with about 300,000 sites. This as the data set tends to vary with how conservative you are about calling the sites, and also how many, how much missing data you allow in your data set. Oh, and I should say these are all, this is constructed with XML, and it's all 100% bootstrap supported every node. So how about branch lengths and divergence states? This is the second question I always get. This is what I'm going to say. It's good so far. So for all the simulations that I've done, if I put a tree in and I simulate a genome and I simulate next-gen data and I run scissors and I analyze the data, all the trees look exactly like what I put in. So this is really good so far, but I haven't done any, I don't have any pretty graphs to show you. So that's coming soon, hopefully. But I will show you a tree for, this is the same different data. So the nice thing about shotgun data is you can pull out whatever data you want using scissors. So this is the tree, I can say, that got this whole project started. This is a tree for leishmania, which causes leishmaniasis. And you can see this tree is completely resolved, but I'd like to use it as an example. So we used all the same data to estimate this whole tree, but if you were interested in the deep nodes, or for example, if you're interested in the relationships among eukaryotes or any sort of deep time, you might not see those well-resolved nodes. And so what you might want to do is look at different data to resolve those nodes compared to the data that you want to resolve the relationships within this plate or within this plate. So what we can do with scissors is we can do exactly that. We pull out different data to look at different relationships, deep time, different plates, etc. And what you'll notice is this is the exact same tree, again with 100% bootstrap support, but I've grouped each of these into single taxa. And so it produces the same tree. Incidentally, it produces pretty much the same branch lengths. And so if you're looking at deep time, you can group things differently, produce different data sets that are appropriate to do phylogenetics for the taxa that you're interested in. And so with that, this is the conclusion. This is your full take-home message. We have a new way to rapidly identify phylogenetically informative data directly from the raw reads. No assembly, no annotation, no alignment, no identification of orthologous genes, and so on and so forth. So this is freely available. Please come talk to me if you want to use it. I'm happy to help you out or adjust as needed. Kelly Harkins is the grad student that really got this project going by sequencing leishmania. She works in Ann Stone's lab at ASU. Cartwright lab has been very supportive and helpful. The European Nucleotide Archive is where I got all of my data. So again, a plug for reusable data. Our funding sources, we have been recommended for funding by NSF, so hopefully we have 3 more years to work on this project. And I work in the lab of Reed Cartwright, and he's always looking for really good postdocs for computational positions. So thank you.
Do you know how well your method would do with handling a genome that has a lot of, like when doing composite genomes, would you come into problems if there were like a whole genome duplication event happening somewhere in the history of those taxa? Like, will it collapse those?
Yeah, so it should, presumably it will collapse those to a certain extent. You'll probably get breaks, so you don't have the short contigs. When you do the alignment back, if you have variation at sites, then those sites would not be highly conserved and those would get thrown out. So if you have duplication events, if you have polyploid genes, it should be okay because the variable